Hello, it's Keith here, and this is lesson 1 of the multi-platform series of my PDP11 programming tutorials. What are the multi-platform series? Well, this series we look at little programming examples that only really rely on the functionality of the processor. Now, today we're looking at these examples on the UKNC, but they will work on any PDP11 processor-based system. What we're looking at today is a range checking routine for checking if a target and a pointer are within a certain range, and a random number generation routine, and these are going to be used later to produce my little game called Suck Shoot. Now you can see an early version of the game here. The game's already actually finished. This is a sort of prototype version to show off today's code. Now we are randomly positioning our bat here, and then when our cursor gets within range of that bat, the bat is disappearing and moving to a new random position, and so later on the bat will start to fly towards the screen and the player will have to get in range and shoot the bat to continue. So this is, as I say, some template code that we're going to see built into a game later on, but as I say, the code we're using today is not reliant on the UKNC. It will work on a regular PDP11 server if you have one of those, so hopefully should be useful to anyone who's looking at PDP11 programming. Now, as I always say, the random number generator we're looking at today categorically is not the best. It's one that I've ported from all of my other systems. I write a pseudo-random number generator on all of my systems that hopefully produces the same random numbers on all of my systems given the same random seed. The idea is I could create a game with 65,000 random levels all created from a single random seed, and those levels would appear on all of the systems in exactly the same way because the random number generator produces the random numbers in the same way on all the systems. So it's certainly not the best, but if you need a random number generator, it certainly does work. Now, today's example, we're taking the 16-bit random numbers that the generator outputs and converting them to just 8 bits for convenience, but the generator itself takes a 16-bit random seed and produces 16-bit random values if you need them. Okay, well, let's go over to the code and let's take a look at how it works. Over we go. Okay, so the code we're looking at today is going to be split into two parts. The first part we're looking at is this random.mac file here. This is the random number generator itself, and then the range checker, very simple bit of code we're just going to have a look at later. So the random number generator basically produces 2 bytes in 2 separate ways. If you were using 16-bit numbers, you would use these as 2 separate parts. If you are using 8-bit numbers, these two are XORed together to create the final byte. Now, as part of the random number generator, we are using 2 random number tables. They are 16 bytes each. Here are the bytes, and as I say, these are the same on every system. So that's how we produce one of the bytes. The other byte is actually made up just by repeated rotations and XORing the 2 random seed bytes together. Okay, so as I say, the random number generator is designed to work in words. It's designed to work from a 16-bit seed and provide 2 8-bit values. Now, to maintain compatibility with the other versions of our code, we're passing our 16-bit seed in the register R1, but we're actually returning the 2 byte values back in 2 separate registers, R3 and R5. This is so that the random number generator produces values in a similar way to the other versions of the code. As I say, it was originally an 8-bit routine, and so it was being passed BC on the Z80, and it was returning its result in H and L, I think it was. That's why we've got it split out in a little bit of an odd way. So basically, the do random version will produce just a single byte. It automatically increments the seed each time, so it's the simplest one for us to use, and that's the one that we're using to move our bat around the screen. Now, all this does is it basically increments the random seed. The random seed is stored at a memory address here. It's a 16-bit random number. It's incremented each time. We then do the random routine. We are then basically combining the 2 bytes, XORing the 2 bytes that are returned together and returning that value in R0. And you can see we're backing up a variety of other registers so that nothing is changed except for R0 by running this routine to make it nice and easy to use when we are running this as part of our program. Now, do random word will, as I say, take R1 and produce R3 and R5 from it. We use 2 functions to do this. We are using rbyte1 and rbyte2, and rbyte2 will return the value for R5, and rbyte1 will return the value for R3. Okay, these work in 2 very different ways. Now, first what we're doing here is we are splitting R1 into 2 parts because it's a 16-bit value, but as I say, this was all based on Z80 functionality, 8-bit functionality. So we are taking the high byte of R1 and we're moving it into R4 here. So R1 contains the low byte and R4 contains the high byte, and then we are masking those so that we've only got 1 byte each at the start of R byte 1 here. So that's what we're doing there. And we are then going to use this and we are going to create some random numbers. Now, as I say, this is based on Z80 functionality, and so the Z80 has an RRCA command, and this will rotate the bits around a byte without losing any. And so we're mimicking this functionality here on the PDP11. We are rotating the bits in R0, and that is pushing one bit out. But to mimic RRCA, we are then putting that bit in by using the bit set command to set bit 7 of the byte if the carry was set by that rotate command. And so this is effectively a rotate command that is never letting any bits leave the byte. They're just going round and round in circles, which is the functionality that this RRCA command had on the Z80. So we are mimicking that command so we can easily port this code and get the same values out. So that's what we're doing here. We're rotating the byte in R1 twice here. We're then XORing the byte in R1, that's one of our random seeds, with the value now in R0. We're doing 2 more rotates. We're then XORing the second seed byte with R0. We're doing another rotation, and then we are basically XORing in this fixed value here. And this is all just to give a nice random looking value, because basically the first time we run this routine we would expect our initial seed value to be either a 0 or 1. I would think it'll actually be a 1 in this case, but to make the initial value look fairly random we need to, you know, XOR in some fairly random values just to give it an appearance of some randomness in the start. Now this first routine is very much based on the ZX Spectrum one. It's not the same algorithm by any extent, but the Spectrum random number generator, it would do a variety of rotations and XORing in of values to give a nice random looking value there. So that's how we are getting our first byte. Now, if we were to do the same kind of thing for the second byte, then we would get 2 random number bytes that would very much follow a similar pattern, and that's not going to be very good for us because we want those 2 bytes to look like they are unrelated to each other, even though the seed they were created from has hardly changed with each iteration, and the top byte of that, if we are inking a 16-bit value only by 1 each time, is going to remain 0 for an awful long time. So what I'm doing here is I'm using those 2 random number tables here. So we're going to use these to get our second random numbers, and that's what we're doing here. So we're getting the address of that random number table here. We are then taking one of our random values here, and we're then XORing it with this fixed number here. And we're then just making sure we're only keeping the bottom 4 bits here. And we're going to use these as an offset to our lookup table. And so we're going to look up a byte based on this randomly generated offset here. This pseudo-randomly generated offset, I should say. And we're going to read in a byte into R2 here from that first lookup table here. So that has read in from rand 1, one of these bytes here. We're then going to use the actual first random number generator we had here. So we're using this one to create a second lookup byte. We're then again keeping only the bottom 4 bits because we've only got 16 entries in our lookup table. And we're using an entry from the second lookup table. And then basically what we're doing here is we are XORing those 2 together. And we're clearing the top byte because we only want a 1 byte value, because of course PDP11 in a lot of cases is working in 16 bits, but we only want an 8-bit value to maintain compatibility with our other systems. So we're clearing the other bits and then we're returning, and so that is returning the second byte in R0, and that's what we're combining together to do our random number generation. Now when we want to randomly position our enemy in our little suck shoot game that is, say at this stage, is a work in progress, at least as we see it here. So the game is finished and you will see the full game later on, but this is the incomplete version by design. So when we are generating a new position for the bat, we need to make sure the bat is on the screen. So we've got this function called ranged random, and this is taking a maximum and a minimum that is an acceptable returned byte that the random number generator will produce. And so this is being used. It's very, very simple. All it's doing is it's using the random number generator. It's checking if the value is below the acceptable minimum. And if it is, it's going back and generating another random number. And then it's checking if it's above the acceptable maximum. It's just repeating until it gets a valid value. And The reason that this random number generator is at least acceptable is because it will eventually produce all possible outcomes. So even if it takes a while to get a valid random number, it will eventually get one, even if you give it a range in which only a single value is acceptable. A poor random number generator would be one that never produces every possible byte value in the range of 0 to 255 or 0 to 65535. And that is dangerous because you might end up with games that lock up because, as I say, if through a variety of circumstances only one possible value is acceptable as an output from the random number generator and the random generator physically cannot output that value, you're going to have a bad day. So that's how our random number generator is working. So that's random number generation. Now the other thing we are doing is range checking, and this is how we are testing to see if our player's sprite is within the range of the enemy. That's what we're doing here. We've got our player X and our player Y here, and we are just moving those into R0 and R1. We are moving our enemy position into R2 and R3. And we are specifying our range in width and height. Now the width is in byte and the height is in lines, so the width is much smaller, the acceptable range, than the height. So we're basically going to see if the player X and Y is within this range of the enemy X and Y. And that's what this range test routine is going to do. And it's going to set the carry if the player is in range of the enemy. And in this case, what we're going to do is we are going to re-randomize the enemy if the player is within range. And that's why when we run our little game, or our would-be game, our will-be game, then when our player sprite gets within the range of the bat disappears to a new position. Now in the final version, we will only do this check when the player presses fire. So we'll have some kind of gameplay, a very simple game, but it's a proof of concept on this this strange PDP11 based system. I had some fun making it. Okay, well let's first have a look at just a little diagram. And so this is the kind of thing we're doing to achieve our range checking. So here is the one object, and what we're going to do is we're going to check the range and see if the second object is within the X and Y range of the first one. That's what our code is going to do. And how does it do it? Well, it's actually pretty simple. Go away, we don't want to see you again. And it's actually pretty simple. So all we're going to do is we're going to take the X position of the first test object, we're going to subtract the horizontal range, and if we've gone below 0, then we're not going to carry on with the test because that will have invalidated the value. You know, if our test position is very far on the left, we might have gone negative, and that would be testing it very far on the right. We don't want to do that, so we're going to skip over if we have gone negative. Otherwise, we are comparing to the second object, and if we're out of range of that second object, well, clearly there's no point continuing, so we're going to go to this over range. We're going to clear the carry, and that means that the objects are out of range. If the object hasn't currently proved to be out of range, though, we're now going to do a second test. Basically, we started here, we've subtracted the range, so we're now over here. We need to add the range twice to test the other side of the range. That's what we're doing here. We're adding that value twice, and then we're comparing again to the X position of the second object. And if that is out of range, then again we're skipping. But if it's in range on the X axis, then we need to check the y-axis, because it might be way up the top or way up down the bottom, out of range on the y-axis, even if it's within the range on the x-axis. And so we're now doing, well, basically the exact same thing, just with the range height and the y-axis. So we're basically subtracting the y range from the y position of the first object. We're then comparing to the y position of the second object. We are again checking to see if we've gone negative, because that would have gone below 0 and gone back to a very high value. And then we're again adding the height of the range, moving down and testing the other side of that with the y position of the second object. Now, if at no point here we have gone out of range, then we're clearly in range on all sides of our object. In that case, we are setting the carry and we're returning, and that is saying that the two objects are within the specified range. And so that's how we are doing this. And in this case, for this game, we're using it to detect when the player has shot the bat. But I've used this same kind of algorithm in other games, like my little Y-Quest game, where this was being used to detect if the enemy had hit the player, and you can use it for anything similar to that. You can also use it for if you need an AI routine to make the enemy decide when to turn or target an enemy or a player or something. You can use it as part of that kind of logic to say, well, you know, is the player within range? Is there a wall in range? Do I need to turn around? That kind of thing. Very simple little program, but a little routine. But as I say, it'll do in an emergency. And I've written a few little games with these. I've used both of these kind of routines in a variety of games So maybe there's some use to you. As I say, I'm not trying to make it out that they're best in the world. They may even be the worst, but they will certainly work if you have nothing else. So if you want to have a go with them, please go to my website and download them. You can download the source code for these examples you've seen today, and in a little moment you'll be able to see the full suck shoot game as well. Now, if you've liked what you've seen, please like and subscribe. Especially make sure you subscribe, because as I say, we're going to be doing more of this PDP11 UKNC thing, and we're going to be getting that full suck shoot game working, including sound. I've got a sound driver, my Chibi sound driver, which I port to all of my systems. I've actually got working on the UKNC, which I was feeling quite smug about, because I didn't think I'd be able to do it because it's such a weird system, but I managed to get it working, so we'll see that as well. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.